Oh,
More DP.
Those problems were really weird. I actually have no
Okay.
edit distance.
Okay. How about I propose this? We go through Knapsack, and because it's on the P set, right? Not Knapsack, but a variation of it. If we have time, we do a couple variations. If not, maybe not. And if we have time, we do edit distance. Let's see what happens after Knapsack. How many people got the difference between polynomial and pseudo-polynomial? Okay, so we should definitely do Knapsack.
Constant factors, they don't matter. Oh wait, yeah, of course, yeah, they do.
It's not a. So the thing is, it's not constant factors. That s there is not a constant. Okay, so the knapsack problem. So the way I look at it, you're a thief. You somehow made your way into a vault. That vault has n items.
Way better than camping.
Each item has a weight of SI pounds. And after you get out of the vault, assuming you make it alive and everything, you can sell it for VI dollars on the market. So this is how much money you get out of it. VI. All right, well, now the problem is the only thing that you have with you as you enter that vault is one knapsack that can carry at most S pounds. If you try to put more stuff in it, so if you try to load it up with more than S pounds, it's going to break as you try to escape from the vault, and stuff is going to fall on the floor, and then many laser beams will shred you to pieces. So that's undesirable. So we can only load the knapsack with S pounds. Now, given this restriction, we want to make as much money as possible out of the whole thing. So we want to load up the knapsack optimally. Okay, does this make sense? Everyone remembers? All right. Good. So 2 ways to solve it. Graphs and dynamic programming. We're going to do both. Who wants to go for graphs first? Who wants? OK, never mind. Majority has been achieved. So, how do we represent this? First off, let's represent the solution. So a solution is which items we choose, right? So we can phrase this as n decisions. Each decision is a true-false decision, and it indicates if you take that item with you or not. So DI says, do I take item I? So now this looks more like a game. You're on a TV, there's a game show, and you get asked n questions. Do you want to take this item with you? Yes or no? If you somehow manage to get items that are more than S pounds heavy, you get shot, you don't make it to the end of the game. Otherwise, when you leave the game, you make some money, and the money that you make depends on what items you took with you. So now this looks like the game problems that we used to solve with graphs, in that you have decisions, those decisions are moves, and they get you through a graph of states. Now let's see what's in the state. So what do we need to keep track of? First, we need to keep track of what item we're thinking about, right? And then there's something else that we need to keep track of. So, state.
How much weight is the, like, how much capacity we have?
Yep, very good. So the reason I need that is when I'm deciding whether I'm taking an item or not, I want to know if I'm going to get shot or not. So if I take too much stuff, I'm not going to make it. So I need to know if this item fits in my backpack or not. That's equivalent to knowing how much weight I have left. So S pounds, let's see, this is capacity. So how much weight left in my backpack's capacity. And this is equivalent to how much weight I have accumulated, right? The total weight of my items. Weight of the items I have taken so far. Okay. So the sum of the weights of the taken items. Right, if I know...
Isn't it like the total minus?
Well, I'm saying they're equivalent. So if you know one, you can compute the other.
Oh.
Sorry, they're not equal. They're just knowing one lets you know the other one. But this is more useful in terms of putting the graph together, I claim. We'll see if that is true or not as we try to put the graph together. So what's a node? What's an edge?
An edge is putting in one more item.
Okay.
And a node is a state.
So what's the weight going to be on an edge? If the edge means I'm taking an item, then the weight is going to be what?
The weight of the item you're at.
The earning associated with that.
Yeah. So I like this better because in the end, my goal is to maximize earnings, right? And I'm going to feed my graph to a shortest path algorithm. Maximize earnings, minimize path weight. They're the same issue, flip signs. So I'm going to say this is the value of the item. Almost. Does this work or not? Negative value of the item. I have to flip the signs to turn it from a maximization problem to a minimization problem. So shortest path will give me the shortest path, right? That's going to correspond to making the least amount of money if I don't add this minus sign. Okay, so what's a node?
A unique set of items.
Sorry?
A unique set of items.
Okay, so the state in a node is going to have I, which is the item that I'm looking at, because this way I'm going to have one node for each item. And what else did I say I need to keep track of?
Some of the weight of the taken items.
Yep. Weight of taken. So this is sort of like the gas problem where you have to keep track of how much gas you have as well as where you are on the map. Sorry if it brings bad memories. Let's talk about an example so that we can draw a graph for it and see what things look like. So say we have 3 items, and say our backpack has 5 pounds. And my 3 items are golden statue, value 10, weight 4 pounds.
What?
These are $1,800 when money actually used to be worth something. Crystal ball. You can sell this for $4 and it weighs 2 pounds. And someone in the previous section wanted a fountain pen, so we're going to use a fountain pen. That's worth $7. Culture is worth a lot of money, right? And weighs 3 pounds. Really ancient fountain pen. I don't know how people wrote with it. Oh well. So how do we draw the graph for this?
So we
You could
do
make a
three
tree.
nodes then?
Just make a tree that where each level of the tree is take item I or don't take item I. Make a big binary tree. Does that make sense?
Yes, but that's gonna. So if each level of the tree says that whether I'm taking an item or not, and then I have 2 descendants, then that's going to be 2 to the number of items. So that's going to be exponentially in the number of items, whereas we're going to end up in a solution that's where the running time is proportional to the number of items. I mean, it makes sense in some cases, if you have fractional costs or something. By the way, all these weights are integers. Sorry, I didn't mention that. So my bad. OK. But I like the idea of having some sort of levels based on items. So let's say I'm going to have a starting node. And then I'm going to have some sort of layer for item 1, some sort of layer for item 2, and some sort of layer for item 3. Right? Some sort of vertical layer. How many nodes do I have in a layer? One node for each possible weight, because I promised that in a node I keep track of the item that I'm considering and the weight of the items I've taken so far. Right? How many possible weights do I have here?
3 weights.
You can sum also, right?
So
Oh,
my
I see.
backpack holds 5 pounds.
Oh, I see.
So then, what are the possible sums I can get? How many?
4. 'Cause there's also 5. 4, 2, 3, 5.
Okay, who bids? I heard so far. I heard 2, 3, 4, 5, 6. Who wants to bid more?
Not more than 6.
So the answer is 6, right? The possible weights are from 0, which is an empty knapsack, until 6, which until weight 5, which is a full knapsack. So weight 0, 1, 2, 3, 4, 5, 6. And I'm going to start drawing the nodes.
Could have weight 10. So like,
Well,
I mean,
we're,
no, sorry.
we're never going to fill up a knapsack with more than 5, right? Otherwise, we're going to die.
Then why do you
Why do we
have
have
6?
6 then?
Because I can't think. Thank you. OK, so this node, the first node, weight in the backpack, 0. We're looking at item 1, right? It's connected to the starting node. What outgoing edges do I have? So what do I do with item 1? I can take it or not take it. OK,
It's a start. 4, 2, 3.
for
You connect the edges to 4, 2, 3.
to 4.
Oh. Am I answering the different question?
If it's item 1, you should have a weight.
So the nodes have 2 numbers in them, I and j. Oh, sorry, there's the wrong order here. 1, 0. So I'm looking at item 1. So far, I have 0 pounds in my backpack. Looking at item 2 with 0 pounds. Looking at item 3 with 0 pounds. Looking at item 1 with 1 pound in my backpack. Item 2 with 1 pound. Item 3 with 1 pound. So on and so forth. So if I'm looking at item 1, and I have 0 pounds in my backpack so far, what happens if I don't take item 1? Where do I end up?
2, 0.
Yep. So I'm looking at item 2 after I'm done deciding what do I do with item 1. And if I don't take item 1, then I'm not going to have anything in my backpack. So this edge corresponds to we don't take 1. What if I want to take item 1? Where do I land?
2, 4.
All right. 2, 3, 2, 4. So if I did take item 1, then I had 0 pounds in my backpack before. Now I have 4 pounds, and I'm still considering item 2. What about edge weights? What's the weight of the edge that says I don't take item 1? What's the edge weight of the edge that says I do take item 1?
0 and 10.
Negative 10.
Minus 10.
Minus 10.
All right. 0 and minus 10. That minus lets us get the shortest path. Now suppose I'm in 2, 0. What are the outgoing edges?
This is the same as making a giant binary tree. Right?
So here some of the nodes are going to overlap. Sorry, some of the edges are going to, it's not going to be a tree. Because I can have multiple paths from a root to some node.
But this looks like it's taking the same complexity is building the tree. If you were to carefully build the tree so that you don't have infeasible solutions on the tree.
Well, then you're actually doing dynamic programming. You're not building the tree if you're doing that.
Oh, well, in that case.
So you're still converging to this. Yeah. You're probably thinking this and you said decision tree, binary decision tree. Or at least that's what I understood. So you're probably thinking of the right thing. Okay, we can see if we're thinking the same thing when we end up looking at the running time. Yes.
So the goal here is to maximize, have the most valuable items possible in the back, like in terms of money.
Yeah.
Okay, so the weight from the -10 weight that you had there was because that item was $10.
Yep. And in the end, we're going to give the graph to a shortest path algorithm. So yeah, speaking of the goal, what's the answer here, by the way? 11. How do I get 11?
By taking the last two items.
So I take the ball and the pen and I get 11, right? Okay, everyone on the same page? All right, so I'm at item 2. I have 0 pounds in my backpack. What are my outgoing edges?
And 2, 3, 2. Oh wait, sorry. What's the third item?
Second item. You can.
Yeah, sorry. Yeah. Wait, no, shouldn't be 3, 3 because the third item has 3 pounds.
Well, I said I'm looking at the second item and then I'm deciding where I'm going.
Yeah.
So this graph has a problem that when I get to the third item, what do I do? So I need one more layer here, which means that I'm done.
Oh no, I was saying that if the outgoing edge from 2, 0, it's the weight of the taken item. So if you decide to take the third item, shouldn't the outgoing edge go to 3, 3, not 3, 2?
But when I'm at layer 2, I'm only looking at item 2. So I'm looking at the items in sequence. First, I have to decide, am I taking item 1? Then I decide, am I taking item 2? And then I'm deciding, am I taking item 3?
Oh,
While I'm here, I don't see item 3. I only see item 2.
Aren't those weights on the left side then?
Oh, no. Yeah, these are backpack weights.
Oh, it's 2 pounds.
Oh,
Oh,
I see.
okay.
Okay, so it's 2.
Yeah, so down here, these are pounds, and these are items. Okay, what are the weights on the edges? Okay. How about the southern node, 2, 4? What are the edges coming out of it?
0.
3, 4.
3, 4.
So if I decide I'm not going to take item 2, but I already have 4 pounds in my backpack, I'm still going to end up with 4 pounds in my backpack.
Oh yeah.
And I don't get anything out of it. And that's it, because if I try to take the second item, that would put me overweight. So the edge would go out of the graph, therefore it doesn't exist.
You can remove it and then go back to 3, 0. Right? Or is that not allowed?
No, because when I'm here, I don't know how I got here. I don't know if I had item 1 or not.
Oh, okay. Okay.
So the benefit of doing it this way is here I'm just looking at item 2. I do not know how I got there. I do not care what I'm going to do later. I'm just looking at one item and making one decision based on that. So does this make sense? Where do I get my answer from?
Can you have like a final node on the right side?
Okay, so one way of doing it is that I'm going to have a final node on the right side and connecting everything to it.
Do you need the done nodes right there, or could you have just skipped done and connected 3 to that?
So I can do that, but then it's going to be hard to reason about edges. This makes it easier to reason about edges, because when I'm looking at this layer, I'm still going to have edges deciding whether I take item 3 or not. So it would be confusing to have all the edges pointing to the same place. I can, it's just that the graph would look more confusing. So by the way, if I'm at 3, 2, what are the outgoing edges from 3, 2?
It's just all horizontal, right? You can't take
So
any more
I
than-
can be done with 2 pounds, and that means I get 0, or I can take item 3, and then where do I land?
With weight -7.
Okay, does this make sense now? Somewhat?
So for this dynamic programming style.
We'll get there in a bit. Before, let's see what's the running time for this. So one way of finishing this up is we connect everything to one destination node. Another way of doing it is that we connect the source node to everything here. With edges of cost 0. And say, well, this is how much weight we're going to waste. So if my solution path goes here and then goes somewhere through the graph, it means that I'm going to waste 1 pound of capacity. So my backpack is going to have 4 pounds when I'm done.
Would it be 0 or infinity?
What should the weights be? Good question.
Like, because this is not possible, right, to get from S to 1, 1.
So I was saying that if I get from S to 1, 1, this means that I'm wasting a pound. So my backpack will have 4 pounds of stuff, and then 1 pound of capacity will go to waste.
Isn't there another way to waste it? On the right side?
So
You end at the top? Or not at the bottom, basically?
Yeah.
So you're not like double counting in terms of like losing stuff? So
Um,
you're like losing weight on the left. You're representing losing weight on the left side and the right side.
Well, so if I represent losing weight on the left side, then the advantage is that I have a single destination node. What is it?
That dot.
So this is the source.
Down the bottom, down 5.
The destination is this guy, right? I can waste capacity here. So that means I can say that on this side, I don't need to waste stuff. On this side, I need to arrive at done 5.
Oh.
So that's the advantage of doing it this way, aside from the fact that it's going to map to dynamic programming. So there are many ways of doing it. I can choose to connect the source to 1, 0, and then look at all the paths here and choose the best one. I can connect the source to everything here with paths of some weight, which you guys still need to tell me what it is. And then I can look at the answer here.
Oh, cost 0.
Thank you. So this is another way. And yet the third way would be to only connect the source to the first node, and then connect all these done nodes to another node with cost 0. And this is equivalent to this. The reason we're doing it this way is because this maps to dynamic programming.
Easier. Wait.
It maps closely to what the DP runs, to how the
I mean,
DP runs.
there's like multiple. You could have. Is it possible to do the DP such that you do it the other way as well?
Yeah.
Okay.
Yeah, you can flip the DP around too. Okay, how are we doing with this? So then I hope the running time analysis will go really fast. How many vertices?
Or 3.
Okay, so V is,
MS.
so
Or
n
MS
layers,
is
right?
the size of your backpack.
n plus 1 layers actually, but,
N times V max.
and
Oh, no, wait, max.
n times capacity, right?
Yeah.
Yep. So it's actually n plus 1 times capacity plus 1. But I don't want to deal with that, so I'm going to use order of so that I don't have to deal with that. How many edges going out of a vertex? Yep. So at most 2 edges per vertex. So how many edges total? Okay. What shortest path algorithm am I going to use?
Bellman Ford.
Topological sort BFS.
Okay, I'm going to choose the second one because it runs faster. So Bellman-Ford's running time is V times E. If I use the DAG algorithm, that means topological sort and then a DFS, that's V plus E. So please, whenever you have a dynamic programming graph, this is the answer. It's never anything else. It's never Dijkstra. It's never Bellman-Ford. It's always this. And this means? So this is the running time of the graph solution.
If you use BFS, do you need to put in the dummy nodes for the edge weights?
If you use BFS. Yes, so then the running time would be bigger than v plus e.
Right, so then the running time depends on s, and you have to multiply by s again?
So this isn't doing BFS. This is doing the shortest path algorithm for direct acyclic graphs. So it's the DAG shortest path.
Right.
Were you here before Thanksgiving?
No.
Right before? Yeah. So you missed the algorithm.
Okay.
It's in the extra lecture notes.
So but basically you don't have to put in all the dummy nodes?
No.
Okay.
No. So you do a topological sort, and then you only consider a node once, and you look at all the edges coming through it and make a decision based on that. Yep. All right. So this is the running time, this is the algorithm, this is the solution. What if we do dynamic programming instead? Instead of nodes, we have subproblems, right? A subproblem maps to a node. So the same things that we decided about the state that we store in a node is going to apply, the same things are going to apply to the state that we have in a subproblem. So what are the subproblems? Okay, first off, how many subproblems am I going to have?
NS.
So I just said that one subproblem will map to a vertex in the graph. NS vertices, NS subproblems, right? Come on, guys, bear with me. Get more cookies. Are the cookies still there? Please pass them around and eat them. Okay, yes?
So one subproblem would be getting the, I guess, lowest, or like most amount of money for that given week, or for that total week. So like at week one, like a £1 or something, you want to figure out like how much.
Okay, I like that. So let's start writing. So what is the maximum value that I can get using a certain weight? So some weight. And so if I label the nodes using indices ij, I'm also going to label the subproblems using ij. So I'm going to say that subproblem ij is what's the maximum amount of money I can get by using a weight of at most j, and you said something about items, so we have to figure out which items. Which items? Anyone else can help her. You already did the hard work, so you have most of the stuff filled in. So feel free to jump in.
Greater than or equal to I.
Okay. Sounds good. So we're going to number the items starting from 0 this time because we're going to have a dynamic programming table, and that means we like 0-based indexing. So the items are going to be 0, 1, and 2. 0 is the statue, 1 is the ball, and 2 is the pen. And this means we're going to look at suffixes of items, right? First, the empty set, no item. Then only the pen. Then the ball and the pen. And then the statue, the ball, and the pen. And we're also going to consider what weights, how much weight we have in our backpack. OK, so let me write this again. 0, 1, 2 here. And weights 0, 1, 2, 3, 4, 5. And this is going to be our DP table. Now, how are we going to compute this? dp of ij is? All right, the maximum of something. Good. Perfect way to start. How many decisions do we have?
2.
2. It's the same as in the graph problem, right? Once we solve that, this should be pretty easy because it's really very similar. So the 2 decisions are, do I take item I, do I not take item I, right? If I don't take item I, where do I what situation do I land in? So suppose I don't take item I. Okay. I plus 1. So I have to make my answer, make up my answer using items I plus 1 all the way through n minus 1. And how much weight do they have to have? Yep. Now suppose I do take item I. What happens?
No. Wait.
So you're thinking of the right thing. We're making some money, right?
Value I.
Value I. So this is how much money we're making. Good.
Plus dp I plus 1. J minus weight I.
Make sense? Okay, now I only have to do one more thing to make sure this code doesn't crash.
Sorry, what's the second? We have the third term for?
Okay, so this is, I'm making some money, right?
Yeah.
This means I'm going to have to look at the items starting from I plus 1 and n minus 1. And now I took item I, so that means I have SI pounds in my backpack.
Yeah.
So the remaining items must weight J minus SI pounds.
Okay.
Because I'm going to add the SI pounds for this item, and in total I'm going to have at most J pounds. Make some money, lose some capacity.
Did we switch the order of the
Yep.
directions of the arrows?
Yep. This is what happens when you move from the graph to dynamic programming. Or you can draw the graph the other way around.
So could you have also done plus SI and then done something else as well?
Sorry, plus SI.
If you did plus SI and then you did some other check case, that was different.
Well, I do need to make a check.
Yeah, so that's greater than or equal to 0.
This thing, right? Because otherwise the code is going to crash. So J minus SI is greater or equal to 0. I think this means J is greater or equal to SI. Right?
Yes.
Okay. So yeah, so when I have the graph, at least for me, the natural order when I have the graph is to consider the moves that I'm making in the game. So I'm answering the questions one by one. Do I take this item? Do I not take this item? When I'm in the DP, then when I make a decision, I want to have the full information on that decision. So whether I take the item or not depends on what would happen with the items following it. So representing it this way allows me to make the decision right here.
If we've done prefixes rather than suffixes, we could have done it the same.
It would have been exactly the same as there, yep. Yeah, so we taught dynamic programming over many years, and it turns out that people understand suffixes better than prefixes, and the graph format makes more sense that way, so that's why we're doing it this way. It's for your own sake, trust me. Or at least we think so.
Where does suffix come in? I know what it means, but...
These guys.
Oh, okay.
So these are the subproblems. Nothing, item 2, items 1, 2, 0, 1, 2. So it's a suffix of the set of items.
How can you going backwards rather than forward?
Yep.
It doesn't actually matter.
Uh,
It doesn't actually matter if we go backwards or forwards.
Yep. In the end, we're going to look at everything. Okay, so we need two things. We need to know where's the answer going to be. And we need to know what are the initial conditions. Oh, actually, I lied. We also need a topological sort. So where do we want to start?
First one.
Okay, where's the answer?
That's it.
Yes?
It's in the lower corner, right? Lower right-hand corner. I mean, if we have all the figures. Oh, we don't have a done column, do we?
Nope.
Oh.
Well, so the answer will have considered all the items, right?
Top left.
So which I? Okay, almost. So top left corner means I've looked at all the items and I have an empty knapsack.
Oh, so the max of all of the first column?
That sounds better.
So the max of all columns would be the answer if the weight here would be equal. But I said the weight has to be smaller or equal. So the answer is easier. I don't have to do a max.
Bottom left corner.
I can only look here. So this means that I will use a weight of at most S, right? Because this is S. And I will have considered items 0 and larger, so all the items. So this is where the answer is. And in general terms, that means dp of what and what. So what's the bottom left corner?
0S.
Yep.
Can you explain again why we did TP 0S?
So I think it's easier to look at 0s and see how it maps to the subproblem. And then convince yourself that this is the answer. So let's do that. dp of 0s means I is 0, j is s. Right? So this is going to tell me what is the maximum amount of dollars I can get by using a weight of at most s. Agrees with the initial problem. And using items I or greater than I. So 0 or more. So items 0 through n minus 1. These are all the items. This is the maximum capacity. So this maps to the initial problem. And that's why I did this. That's why I don't have an equal sign here.
And if you did have an equal sign, then you would be changing your subproblems?
The recursion stays the same, but I have to look at all these to get the maximum. Someone suggested that.
Yeah, if you put an equals there, I mean, you're gonna have to do something to the dp such that the equals actually is calculated, because you can't just arbitrarily.
What do you think of this?
So yeah, something there is going to change, isn't it?
Nope. I think this works. This stays the same, no matter what the sign is. The only thing that changes is where's the answer and what are the initial conditions.
Oh, so there's something else to change. Okay.
Yep. Initial conditions.
Okay.
Yep. Good. I like that you're thinking about that because the next problem changes pretty much that. The sign changes and then these change. Okay, so what's a good topological sort? This should be pretty easy. So if I want to generate a topological sort, what variables do I iterate over and in what order? Okay. And you're pointing you're pointing at n, right?
And down to 0? And minus 1
Okay.
at 0?
Yep. And then the only one left is j. So and then j goes from where to where?
0 to s?
It can go either direction.
Well, yeah.
Can it?
What?
So what do the dependencies look like? When I'm computing ij, I want I
Depends on
plus
something
1
to the right.
and j minus. So I'm looking at lower j's. Higher i's and lower j's.
But it's always higher i's, so doesn't that mean in this for loop that you're already going to have calculated the next right column? So it doesn't matter where in the column? Or am I thinking wrong?
You're right.
Oh.
Fine. Okay, both orders work. I just looked at this because I wanted to have a nice simple. But yeah, okay, fine, both work.
Wait, you mean reversing j works?
Yes. Because we're iterating over I before iterating over j. Of course, this makes more sense. Just because they're both good answers doesn't mean you should choose the one that requires more thinking. I always like the answer that requires the least amount of thinking to prove that it's correct.
You're starting with a full.
I start here.
But if you're going from going from s down to 0, then you're starting down at the corner,
Yep.
which means you have a full knapsack, so that doesn't make sense.
Well, so the argument was when I compute this, I'm looking one right, I plus 1j,
Yeah.
and then I'm looking somewhere here. And I've already computed this column. So it doesn't matter if I go up or down. And that argument is correct. Because first I'm going to compute this column, then this column, then this column, then this column.
Yeah.
By the way, what's this column? This column is the initial condition. So now that we've figured out the topological sort, let's try to compute values here and see what the initial condition should be. So if I want to compute dp of 2, 0, that is the maximum of either dp 3, 0 or something else. This is going to evaluate to false, so it's going to be this. What should the answer be here? 0. So we want dp of 3, 0 to be 0 for this to work. So what's a reasonable initial condition?
Column of 3 is a 0.
dp of n j is 0 for all j. Pretty much what you said in math mode. So I'm going to have an extra column. This is like the done column over there. And here I'm going to say that whenever I'm looking at the empty subset, right? So these are all suffixes. All 3 items, 2 items, 1 item, empty suffix. Whenever I look at the empty suffix, I can fill up a backpack with any weight by using no items. And I'm going to make 0 money. All right? OK, so what are the values here? You guys nodded, so you understood. So then you should be able to dictate the values in the table.
So is that one also 0 because you can't go up
Yep.
to anything? And then the next one is 4 because you can go.
So the next one is,
Or I don't know if it's like
so it's for the fountain pen, right? Last item.
it's like crystal ball. Wait. To go up.
So we're going statue, ball, pen.
And this is weight on the left side, right?
This is, oh, so we're filling them like this in the topological
Oh,
sort
okay.
order that we chose here. We said this is the order, so this is what we're going to use to calculate the table.
Oh, so it's still 0 then.
OK?
7.
So here, this condition is going to evaluate to true finally. So this is going to be the maximum of either dpi plus 1j, so dp of 3, 3, which is 0, or 7 plus dp of 3, 0. So 7 plus 0, which is 7. That's why it's 7. OK. 7, 7. How about this?
0. 0. 4, 4.
The maximum of 0 and 4 plus 0, right? OK.
No. 7.
So it's the maximum of 7 or 4 plus 0. So this is 7.
7. 11.
7 or 4 plus 7. OK? Does this make sense for everyone? Last column. Let's do it.
0. Feels like 0.
All right.
0 again. Why not? 4. How much is this thing like?
4.
4. 7. 10.
Sorry for my handwriting.
And it needs to be 11 because you said that'd be the answer.
All right. So it's 11 because it's either this guy or 10 plus dp of 1, 1. Right? So this guy weighs, the first item weighs 4. So I need to look 1 right and 4 up when adding. OK, does this make sense? Please say yes.
What's the up order again? Because I get like I get how if you're looking horizontally, that's the top thing of the max. It's saying dp of I plus 1j.
Yep, so this is looking horizontally, and this means I did not take item I.
You didn't take item I, but if you are going to take item I, you add the value of I, and then you look back for dp of I plus 1, which is the previous column, and the row, the row number is whatever capacity you have left if you did take it.
Yep.
And so in the case of 3 or 1, 3, like cell 1, 3, then if you took item 1, then capacity you have left is 2. Maybe no, 3. Yeah.
Right, so you said total capacity 3, right?
Yeah.
So if I
Okay.
so if I take item 1, how many pounds does it have?
It has 4.
Statue is 0, ball is 1, pen is 2.
Oh, you're not using.
So I'm using those items, but I'm starting using zero-based indexing.
Oh yeah, yeah. But I mean, we're going from here to here.
Yep.
So I'm saying if you're just you want to pick like the middle cell that's 1, 3. That
Yep.
one.
So this is item 1, so the ball, weight 3. If I take the ball,
You take the ball.
how
that's-
much weight do I have left?
Ball weighs 2 pounds.
Yep.
So you have 3 pounds left, and that's why you're in the 3 column.
Wait, so I have a backpack of 3 pounds,
Mhm.
and then I put a ball of 2 pounds in it. And I have 3 pounds left?
No. Yes, you have 3 pounds left. If you put a ball of 2 pounds in, right?
Okay, so I have a backpack of 3 pounds. I put a ball of 2 pounds. How
Oh,
many
wait.
pounds do I
Wait,
have
so
left
you're saying
of
there's-
capacity?
Oh wait, I thought we had. Oh,
Okay, so backpack, 3 pounds total. I
Yeah.
put a ball in that has 2 pounds. How many pounds?
we have none left. Oh, we can hold 3 total pounds.
Yeah.
Oh, then you have 1 pound left. But we have a 5-pound backpack.
Well, you said we're looking at 3-1. You said we're looking here.
Yeah, we're looking there.
So this means 3-pound backpack,
Oh.
right? Because the subproblem says your weight is at most J.
Got it, okay. Oh, I see. So you're saying J. So J minus SI is saying.
It means you used up, so you put up something there, so you ate some capacity.
Okay, you ate only 2 pounds, so why is it in column 3? I mean, row 3.
Well, you told me to start here.
I know! I'm trying to remember how we got there.
You said, let's start here.
Yeah.
So that's why this arrow points here, 2, 1. Right? You have 2 arrows, 2, 3, and 2, 1.
Because it's J minus SI.
Yep.
Oh, I see, minus 3.
So, like, J is the amount of weight we are left with, right?
So J is the amount of weight I can have for this subproblem. Yeah.
Yeah, like the amount of capacity I have still in my backpack.
Yep. Okay, let's talk about pseudo-polynomial time very quickly and what does it mean, okay? And you guys will promise to look at the recitation notes and look at the other problems, right? So incentive for that. Problem 2 is easier than Knapsack. So if you get that should be a good confirmation that you got Knapsack. Problem 3 is a bit harder than problem 2, but it shows up on interviews. So you want to understand problem 3. I got problem 2 twice in 4 years. So there's a decent chance that you'll get it. So you want to get to problem 3, so you should go through problem 2.
How many times did you got problem 3?
Twice in 4 years.
Oh, okay.
So that's the problem that you want to get to. Problem 2 is a stepping stone. Okay, so running time for dynamic programming. How many subproblems?
Same, and yes.
Yep. Subproblems. How many subproblems do I look at when I compute the answer of a subproblem? 2, right? So order 1. So this is how much time it takes to compute the answer to a subproblem, right? Because I have the max of 2 elements, so it's constant time. So the total running time is? All right. Order of NS. Okay. Is this polynomial? Is this the same kind of algorithm as Dijkstra? Pseudo-polynomial. So the problem is, don't know why. So intuitively, the problem is S shows up in your running time here. And S is the property of your input numbers. It's not how many elements you have in the input. It's what's inside one of those elements. So let's see why that matters. Let's look at the practical example.
How about measuring in cubic inches or cubic centimeters? Is that a problem? It'll take a lot longer if we do it in cubic centimeters.
Yeah, but then you could argue that, hey, if it's an integer amount of cubic inches, you should divide everything by that. So where this really matters is, suppose you have a 100 item input. So 100 items, right? So what's the worst case input on a 32-bit machine? An input looks like this, by the way. How many elements you have, right? So 3. And then for each item, what's the weight and what's the value, right? So then we're going to have 3 weights, which I believe are 4, 2, 3. You guys have to take my word for it. And then I have 3 values, which are 10, 4, 7. Let's not worry about the values. I claim that they're irrelevant. You can convince yourselves afterwards that that is the case. So let's only look at this. The weights have to be between 0 and what for the problem to make sense? If I have a weight bigger than s, I know I'm not going to take that item, right? So how many bits do I need to represent these weights? It's log s plus 1 technically, but if I write order of log s, I'm good.
Well,
So,
times the number of items.
sorry?
Times the number of items.
Yep.
Yeah.
So if I want to represent all of them, I have order of n times log s, plus the number of bits required to represent this, right? This is log n. So log n smaller than n, I'm not going to add it here. So this is my input size. This is how many bits I need for the input. So the worst case input on a 32-bit machine is going to have roughly 3,200 bits. What's the worst case S that I can represent on a 32-bit machine? So these are all 32 bits, 32-bit numbers.
Wait, you mean each of the weights are 32-bit numbers?
Yep.
Okay.
So what's the worst case S I can represent? Which is roughly 4 times 10 to the 9. So the worst case running time is? Roughly ns, right? So n times s, which means roughly 100 times 4 to times 10 to the 9, which means 4 times 10 to the 11 operations. OK, now suppose we're looking at the worst case input on a 64-bit machine. Still 100 items. So what's the input size? OK, so that's how many operations. Let's go through it step by step. How many bits of input?
That's 6,400.
Where does that come from?
100 items times 32 bits.
So yeah, 100 items. Each item weight has 64 bits.
Okay.
What's the worst case S?
2 to the 64.
2 to the 64 minus 1. Doesn't matter too much. It's 1 times 10 to the 19. 1.6 times 10 to the 19. So the worst case running time is 10 to the 21. So what happened? I increased my word size. The running time increased quadratically, right? This is not a polynomial increase. What's the problem here? Why is this the case? If I write log s as b, right, so log s becomes b, what's the input size? Yep, n times log s equals n times b. So this is the input size, right? Now what is the running time?
Number of operations?
Yep.
Oh. Well then it's
N times 2 to the b.
Yep. N times s, right? And s is 2 to the b.
S is 32.
So this is the problem. Right? This is a polynomial in n and b. But here, if I write the input this way, I have b as an exponent. So if I double the number of bits by doubling the field size, my input size, my running time increases quadratically. So this is not polynomial. However, if I write it as order of n times s, this looks like a polynomial. So it looks like a polynomial, but it's not really a polynomial. So that's why it's pseudo, as in fake.
Wait, but so it's actually exponential.
It's not exponential. If we wanted an exponential, so an exponential algorithm for this means try all the possible subsets.
Yes.
And that's order of 2 to the n times n to compute the sum. This is exponential, right? You have n here. It's clear.
Well, no, but like if you have 2 to the b, that seems pretty clear as well.
Well, you have to look inside this s and see what it means. That's the difference. So by increasing the number of items, if you double the number of items, but you don't do anything to the word size, then your running time is going to increase polynomially. But if you change the field size, it's going to increase exponentially. So pseudo-polynomial means watch out, there's a trap. It's not really polynomial. If you increase the input size by increasing the number width, bad stuff is going to happen. So think of Dijkstra. What's the running time of Dijkstra? You count the number of vertices, the number of edges, and you have a polynomial in that, right? You don't have to look at the number size. You don't have to look at any weird stuff like that. Here you do. That's the difference. Okay, does it make more sense? So whenever you have an input number that shows up in your running time, instead of how many numbers you have, that means there's a trap. That's pseudo-polynomial.
It's just like having some constant that depends on something. And
Well, so it's not a constant.
Well, I mean like coefficient.
Once you set it, it's a constant, right?
I mean, that's true for everything, right? You can say that you have 10 to the 80 atoms in the universe, so all the numbers that you work with are at most 10 to the 80, therefore your running time is order 1 no matter what you do, and then running times are no longer useful. So you have to draw a line somewhere.
I think it's just like, well, S, if it depends on your field size and you can scale it, it's kind of like,
So asymptotic running time, what's the point of that? How do our algorithms scale? As our data becomes bigger and bigger, what happens to the running time? This pseudo-polynomial thing tells you that if you're shifting to a larger number size, to a larger word size, then your running time is going to explode. It's not going to scale linearly. Still don't buy it?
I mean, I trust you, I just...
so it's only dependent on the field in this case.
Yep.
I'm not so much
So
arguing.
do you guys want to look over Dijkstra and see what the input to Dijkstra looks like and why that's different? Do you think that's worth your time? Given that this is what's standing between you and the weekend?
What time is it?
If you guys want to, I'm willing to do it. So
4:07. Comes 4:07. I'll stay.
okay. Well, if you guys want to go, you can go. I will draw this for the people who still want to know what it looks like. Dijkstra. What's the input to Dijkstra? It's a graph, right?
Yeah. Nodes and edges.
What does a graph look like? It's some number of nodes. So it's a single number. That's the number of nodes that has log v bits in it. And then for each edge, we have 3 numbers. First vertex, second vertex, and the weight. What are the sizes of these numbers? Log V, and the last one? Okay, and what's W?
Maximum weight.
Yep. So this is... So this is a property of the field size, right? V is not just a property of, well, let's look at V actually. So we have E edges here, right? So the input size is going to be log V bits plus E times log V plus log W. Because I have E edges, right? So I have E of these. I only have one vertex count, but then I have E edges, and each edge has 3 numbers. And these are the widths of the numbers.
These are the adjacent edges to B. Is that right? You say you have E edges.
I'm assuming it's a list. So the most compact representation of edges, I think, well, or it might be a reasonably compact representation, is that you have the list of edges. So you have a graph that has 5 nodes, and then you have an edge that goes from 1 to 2, and then weight 3. An edge that goes from 1 to 5, weight 4.
Number, it's not a, okay.
Well, do I need anything else for vertices? Not really, right?
Wait, so V1 and V2 are neighbors of capital V? Or?
So V1, V2, W, so these are the first edge.
Oh, I see.
So
It's one
each edge has these fields.
Mm-hmm. Oh, and then there's...
So this is the entire graph in one thing.
Yep. This is the entire graph as a list of numbers. And this is how many bits it takes to represent the graph in a reasonably compact representation. Okay, now let's say little v is log v, little w is log w. So then this is order of how many bits do I have here? E times v plus w plus v, right? I just replaced the logs with these variables. This is how many bits. Now, how many operations does the extra take? What's the running time?
Well, I mean, it depends on how
E,
many.
right?
Yeah.
Or
It's V plus E, that's the fastest one, right? But I think you said, like, practically it's only going to be, like...
So this is E plus V log V, the fastest theoretical limit. This is still smaller than E log V. This is going to make my life easier. So this is smaller than this. So if this thing is polynomial, this is polynomial for sure. E log V is E times little v. So how many bits in the input? E times v plus w. How many operations? E times v. Any exponential anywhere here?
If you change the size of V, I think that looks fine.
Just follow them.
Yep. Well, so there is a trick that v is 2 to the v, right? So you can say that this is order of, so this is definitely bigger than 2 to the little v times v. But then you have the same thing in the input. So the input also has at least 2 to the little v times v bits. But don't worry about that. That's too much. So the point is, if you're worrying about this, don't worry. The math still works out. So whatever you have here as an input, the running time is going to be a polynomial in the size of the input. What happens if you double the word size? So what happens if you have bigger weights?
So everything like V is multiplied by 2 and W is multiplied by 2 and in this problem, right? If you're taking,
So if you're doubling the word size, then this is gonna double, this is gonna double.
Yeah.
Everything's fine.
yeah.
If you double, what if you double the size of the weights?
Well, that only adds an extra bit.
Sorry, if you double the size of the weight numbers?
Oh,
So if you move from 32-bit weights to 64-bit weights.
well then instead of, well that's still a constant factor, right?
So what happens to the running time?
No.
Nothing.
Wait,
W does not show up in Dijkstra.
no, that's right.
If it would, then we'd be in trouble. It wouldn't be polynomial anymore.
But practically you will be accessing that number, right?
Yeah, but that shows up in the cost of one operation. So that's why I'm saying this is how many operations you do, how many arithmetic operations. And then the model of computation that we use is RAM, and that says that you can do any math operation in order 1.
In that case, that wasn't what happened.
So here, a number in the input, S, which is the size of a weight, showed up in the running time.
Yeah.
So,
Oh, the size of the input showed up in the running time.
so the size of the input is okay, but one number in the input showed up.
Mm-hmm.
Whereas here, that's not the case. The weights do not show up in the running time.
So why don't we always run the extra then?
So actually, for this problem, for the knapsack problem, you can't find an algorithm that is polynomial. If you do, there's $1 million prize for it because you just proved that P equals NP. So this is the best we can do for knapsack.
Is counting sort of pseudo-linear? Because you need to have a maximum, or maximum, range.
Maximum base.
Does that make sense? For
Counting sort.
depends on your range.
So yeah, but it shows up, the range shows up under a log. So you're allowed to have logs. You're allowed to have log W. You're not allowed to have W. So yeah, it's dependent in the size of the input. If you double the number size, then you're going to have twice as many rounds. But you don't have an exponential number of rounds. Oh, sorry, you're thinking of counting sort. I thought radix sort. Sorry, radix sort doesn't matter because you assume we can do everything in... Oh, never mind. You're right for counting sort. Sorry, no, you're right for counting sort. Sorry, I was confusing counting sort with radix sort. So for counting sort, yeah, it is not linear. It's linear in your range size, which is not linear in the input size. Which is why we don't do counting sort. We do radix sort.
We do counting sort and radix sort.
Yep.
Okay.
But radix sort limits the size of the range, right? That's the point of radix sort. Yeah.
Oh, I see what you're thinking. So doing counting sort with each number.
Right, with really big numbers, takes a really long time.
Yeah, that would take a long time.
Right.
Yep. That is very true. If you try to do pure counting sort on 64-bit numbers, you're going to run out of RAM. Yeah. Okay. Does this make some sense? Okay. Promise to look over the other problems. And in return, given that I didn't have time to cover them here, I promise to answer any emails you guys might ask me over the weekend.
Oh, awesome.
Okay.